My name is Athiray Panchapages, and it's a long name, but if you know X-ray, gamma ray, I go by Athiray. Okay, and today I'm here on behalf of MaGIXS team, so I'll be talking about the MaGIXS sounding rocket experiments. This is started with, this is Marshall Space Flight Center, so in collaboration with SAO and other partnering institutions which are listed here. So I'll start with the science motivation, as Jen and others pointed out. It's known that active regions host high temperature plasma, especially at the core of the loops. And the foot points are relatively at lower temperatures. One of the outstanding questions is what process which is making these hot temperature plasma. And one of the objectives or the way to discriminately measure this is to quantify the relative amount of high temperature plasma. How to do that is to look at a signature called emission measure distribution. And let me take and explain this. What is shown on the x-axis is the temperature of the plasma, and y-axis is the amount of plasma measured integrated along the line of sight and plotted as a function of temperature, what we call it as emission measure. And typically, active regions are known to have like this broken power law distribution with a coolward slope, which is alpha, and a hotward slope, which is beta. And from decades of observation, we know we have a very tightly constrained coolward slope, but what is not known, you can see range of blue curves, which are just betas. And it's been established there is a blind spot with existing instruments which cannot probe these high temperature plasma, which is the smoking gun observation required to detect heating events. And there are several theories which explains how plasma gets heated up, like if you broadly classify them, one says that they are continuously heated, or one says that it is episodical, but it takes high temperatures and then put it in different episodes, which is called low frequency. And to observe that, or to discriminate between these two mechanisms, you need to observe this blind spot area, which we don't have any instruments. And that's what MaGIXS was trying to fill in. It started with around 2010, where the idea started, and observing these is pretty challenging. How we are planning to do is by looking at all these emission lines, which are formed at a various range of temperatures, and I've also color-coded them, which has different ionization potentials, which is also important to do that. So how MaGIXS is trying to do, to observe the soft X-ray spectrum from 6 to 30 angstrom and make unique measurements to distinguish between these low frequency and high frequency competing scenarios. How it is being done is by taking line ratios. We have established that by taking line ratios of elements which are formed at, say, for example, 6.8 in log T and 6.6, that means you are measuring the slope of that. Measuring the slope is directly related to what frequency at which the heating is happening. And second, by looking at the abundances, because several models which have shown that during heating events, abundances do change, there are posters where you can see during flares how things have changed. And during heating events, abundance do change. By looking at all these different ionization potential elements, one can look at the evidence of frequency, and also looking at electron distributions, whether they are Maxwellian or non-Maxwellian, which also tells about heating events which are happening. MaGIXS was originally conceived as a slit spectrometer, as Jen pointed out that, and we have also heard that the challenges faced in slit spectrometer, you have to sit and raster. By the time you will miss a lot of events. So this is the first mission which used X-ray mirrors fabricated from computer numerically controlled CNC polished mandrels, which are used to create X-ray mirrors. They are electroformed nickel optics, which are pioneered at Marshall Space Flight Center. And while we built this experiment, there is also another technology which was developed or pioneered by MaGIXS former PI, Dr. Amy Weinberger, to transform the science from slit to slitless spectroscopy, where you have the spatial spectral overlap data. I'll show you in a minute. And the instrument has become a slitless spectrometer. Up until now, we had 2 successful flights, one in 2021 and one in 2024 last year. And I'll start with this MaGIXS 1. This is the optical layout of MaGIXS 1, which has 3 important sections. The first is the Volta telescope, which is a telescope section. Second is the spectrometer section, which carried electroformed mirrors, parabolic section, and which is sending the beam to the grating, which is a variable line space grating, which disperses the beam onto the third section, which is the detector, which is a low power noise CCD camera developed at Marshall. So the first flight, it's a complicated instrument to align all of these. We performed that, and when we launched, and this is the field which MaGIXS was observed or targeted to observe these two hot active regions, and we, like many instruments, we suffered internal vigneting, and we missed the hot portion of the target which we wanted to observe. However, we met comprehensive success because we did see X-ray spectrum from those two tiny dots, which we call it as X-ray bright points. And not only that, like many people said, sounding rockets are stepping stones for various technology development. This opened up the new technology called inverting of spatial spectral overlap to data, which we got from MaGIXS-1. And this opened up, there are many instruments which are going to come up in the next generation, which are going to use these kind of methods of inversion. So this is the first mission to demonstrate inverting overlapograms. Last time NASA flew these kind of instruments was in 1970s in Skylab, where they had the spatial spectral overlap data. This is the first one in soft X-rays. What you see here is the entire field, which was seen in the previous image. The two X-ray bright points, now you can see they are coming from different emission lines, which are getting overlapped spatially, and that's what is shown. And there are several interesting signs. Though we missed the hot target, we produced several interesting signs from this. One of that is the blind spot. The plot on the right, which is shown here, is exactly the place at the high temperatures. What you see, MaGIXS, the inverted colored lines, shows that the amount of plasma at those temperatures are tightly constrained by MaGIXS observation, which showed that we removed the blind spot which has been from existing instruments. And there are several other interesting results which has come out. Another interesting thing is like how Randy pointed out, looking at these dielectronic satellite lines which Chandra observed, we did see those lines in MaGIXS, and we discovered those lines which are missing in Chianti database, and that also has been added to the solar database. And with MaGIXS-1, since we missed the hot portion, MaGIXS-2 was a reflight, and the lessons learned from MaGIXS-1, we now know how to do slitless spectroscopy, so we modified the instrument design, and that means we removed the spectrometer section, and which made our instrument smaller, lighter, and compact, and that brought us a lot of interesting things, which I'll show you in the next slide. We literally reused many of the components which I've listed here. We have the telescope with the same grating which we used in MaGIXS-1 along with the camera. So we, because we went lighter, so we got 40% more time in our flight. We got close to 7 minutes of observation in flight, and we got a bigger field than what we achieved. And we targeted only one active region. This is the 28 arc-minute field, which is what we observed. And there are several targets. We were lucky to observe many of them during this flight, and including active regions as well as X-ray bright points. Currently, the analysis is underway. So what I want to navigate here, here is the blocked region is the place where it is so complex. There are so many active regions, so many structures. But what you see here, you have several emission lines which are there, and this band of soft X-rays are going to have forest of lines which are useful for characterizing both the temperature and other plasma diagnostics, both in active regions and flares. And we did some initial analysis, and what I'm trying to show here is you can create spectrally pure images across wide range of temperatures. And I also inserted 2 AIA images, which gives you only at few temperatures, whereas MaGIXS can fill the entire temperature space. Not only in temperature, it also has other diagnostics. This is work under progress, and at the end, what I'm trying to convey here is we can remove the blind spot kind of confidently over active regions. Now, another thing is like to find the frequency. We also established by taking line ratios of warm to hot lines, one can get proxies of frequency. That's what is shown here. The left is the AIA image, which shows the high temperature plasma in 94 channel. And we also show the ratio of ion 18 to 17. The hot regions shows high ratios, which indicates low frequency heating scenario. Again, this is a proxy. To get the real frequency, you have to do some modeling efforts, which our team is doing currently. So To compare this, MaGIXS 1 and 2, so we achieved a lot from MaGIXS 1 to MaGIXS 2, increased effective area, higher throughput, bigger field of view, and larger science observation. But we, up until now, we opened that soft X-ray spectroscopy is pretty useful, and slitless confusing spectrographs are very useful to decouple that, and we have a technology to demonstrate, and we demonstrated it with MaGIXS. Up until now, we did that for active regions. Can we do this kind of a design for a flare? And can we demonstrate that? That's what MaGIXS 3 is going to be. I'm the PI for MaGIXS, and we all know that during flares, several physics breaks. Oops, I'm sorry. So there's a movie here. Is it? I don't know whether it's possible to play. Yeah. So what is shown here is a movie of a flare during its evolution. You can see that there are regions, the plot on the black and white shows the regions wherever you see black areas, those are all the regions where we don't have a good measurement of temperature and emission measure. That means you don't have good diagnostics. The purple contour shows the regions with the high intensity, that means they are saturated. But the interesting aspect is the failures are not happening in the same location where you don't have information of the plasma. So temperature changes, composition changes, and MaGIXS 3's goal is to understand the mechanisms that govern the physical processes during the decay of a solar flare, and that's what MaGIXS 3 is going to do. It's joining with the FOXY 5 flare campaign, which we heard from Milo. FOXY is trying to look at the impulsive phase, and MaGIXS is going to look at the decay part of the phase, where abundances are coming back from photospheric to coronal, and we want to measure spatial temporal evolution of temperature and abundances. And that's what is MaGIXS 3, which is a reflight of MaGIXS 2 to demonstrate that slitless spectroscopy for flares. And it's a reflight, so almost all the things we have done the testing alignment of MaGIXS 2, and things are in good shape. So we are going to make some slight modification for our filter optimization, especially to look all these emission lines with good sensitivity, and that's what the optimization we are doing. Also, we are also thinking of looking at a higher cadence capability, less than what we achieved in MaGIXS 1 and 2. By selecting different region of interest, one can achieve less than 1.3 seconds per frame, which would be definitely revolutionizing some of these imaging and spectroscopy in soft X-rays. And I also wanted to start because this idea came from MaGIXS 2. We serendipitously caught a tiny loop brightening, which was equivalent of a B-class flare. You can see that loop coming up. And we did see evidences currently with our existing data, change in abundances with both space and time. And that, we didn't plan for this, so now we are targeting for that with MaGIXS 3. And with this, I'll stop here, and I'll be happy to take questions. Thank you for your attention.